variables and restate the following problem in terms of known and unknown derivatives, but do not solve. How fast is the volume of a cube increasing if its size increase at a rate of 0.5 centimeters? So the key thing is this last sentence here, right? That's what we're trying to break into a given and a want. What are they giving us and what do they want us to find? So let's look at this part right there. If is a general indicator, this is what they're going to give us stuff. If the side increases at a rate of 0.5 centimeters per second. So there we go. So the side, most times we use S for a side, increases at a rate. So that tells you right there it's a rate. So it's going to be ds dt. And we know what it is, 0.5 centimeters per second. So that's our given. ds dt, which is a rate, is 0.5 centimeters per second. So it's increasing, it's positive. It's increasing at 0.5 centimeters every 1 second. Now what do they want? Look at the question. How fast? That sounds like a question. How fast is the volume of cube increasing? So it's volume, which would be V, but increasing, so it's rate again. So it's dv dt. That's what we're looking for. So those are given our wants. Next one was the relation between dv dt, which is the rate of volume, and dr dt, which is the rate of the radius, given volume equals 4/3 pi r cubed. So that's the volume of a sphere. Differentiate v with respect to t. So all they want to do is take the derivative of this guy with respect to t, which is, remember, we're doing related rates, so we're always taking the derivative with respect to t in these problems. So we're given this. Let me space it out. And we want to take a derivative with respect to t, so we're going to do this to both sides. So we're doing some implicit differentiation, right? What's the derivative of v? Well, just like anything, right? The derivative variable is just 1. So that's 1, but wrong variable, so dv dt. So we're going to get 1 dv dt equals, on this side, you're taking the derivative of this guy, so there's only one variable here. Pi is a number, so the only variable is r. So we're going to do what we always do. Bring the power down, subtract 1 off. So we're going to get r squared, wrong variable, dr dt. And then what happens when we brought the 3 down? Well, it canceled out the 3 down here, so we're left with just 4 pi. So there's the answer. That's the relationship between dv dt and dr dt. So let's get to an actual problem. Suppose that water pours into a cylindrical glass of radius 4. The variables v and h denote the volume and the water level at the time respectively. So let's draw what's going on here. So here's my cylinder glass. Ish. We have a radius of 4. So cylinder, radius is 4. Radius up there is also 4. V is the volume, so when I fill this up, how much volume is there? And H knows the volume of the water level. So what happens here is a water level. And from here to here is my H. Right, where volume is like filling it all up, H is how high does the water go. Restate the known and unknown quantities in terms of the derivatives dV and dH of t. How fast is the water level rising if water pours in at a rate of this? So this is actually a question. Like this last part is what we're trying to solve. How fast is the water level rising? The water pours in at a rate of 2 centimeters cubed per minute. So let's break down to what do we want and what's given. So first, how fast is the water level rising? That is saying how fast is this H going up and down. So that's dH dt. It's the rate again. So dH dt is what we're looking for. Water level is going to be H. What do they tell us? If keyword there, if the water pours in at a rate of 2 centimeters per second. Now, water pouring in, if you're not sure what that is, look at the units. That's a cubed. That means volume, right? Area squared. A side is just like this by itself, singular. Well, not singular, but it's usually like there's a power of 1. It's about the best way to say that. Area is squared and volume is cubed. This is a cube, so this is dv dt. So dv dt is 2 centimeters cubed per minute. So that's our relationship. That's what we're given. That's what we want. So I need to find an equation that relates these two. That's the whole point of related rates, right? I got to relate these two things using an equation. Well, we have a cylinder, so it's probably just the volume of the cylinder. And if you remember the volume of the cylinder, volume of anything with a bad V is area of the base times the height. That's how I found the volume of most things unless it's pointing. It's area of the base, which in this case the base is a circle. So pi r squared times the height, which in this case is h. So there's a formula, but I don't have to stop here. I actually know one of these variables. I know the radius. It's always 4. It never changes. This is a cylinder with a radius of 4. So I can simplify this a bit. Plug 4 in, and we have this. That's our equation that's going to relate these two guys. If I want to relate the volume to the height, it's going to be the volume equals 16 pi h. And then now what do? Once we had our equation that relates them, we take the derivative with respect to time. So we're going to constantly do in this lesson. So take the derivative with respect to time. Derivative v is this 1, but wrong variable, dv dt. Over here, there's only one variable, that's h, right? It's like you take a derivative of h, you just get 1. It's like taking a derivative of x. So you get 1 with the number in front, so it's just 16 pi, but wrong variable, so dh dt. Right, all we did is take a derivative. Derivative that's 1, wrong variable. Derivative 16 pi h, it's just a linear term, so it's just 16 pi. But don't forget, wrong variable, right? We're taking respect to t. And now you plug in what you have. We have the volume is 2. So we could plug 2 in right here. 2 equals, that's a bad 2. 2 equals 16 pi dh dt. So then just divide both sides by 16 pi. 2 divided by 16 pi is going to be 2 over 16 pi, also known as 1 over 8 pi. So that'll be my answer. 1 over 8 pi equals dh dt. So that's the rate at which the height is increasing. How fast the water was rising. But don't forget units. Now, generally just don't overthink it. If it's volume, it should be cubed. If it's area, it should be squared. If it's a side, it should just be a linear. It should just be power of 1. So what were units? We're talking about centimeters per minute. So this would be centimeters, and this would be minutes. So centimeters per minute. And that's the answer. Next one, repeat the same problem. So they want the same picture, basically. At what rate is the water pouring in? If the water level rises at a rate of 1 centimeter per minute, then solve it. So let's draw the same picture so we know where we're going. Or a similar picture. Probably a better picture than my last one. So that's 4. Right, so that's the picture we have. And then we have to go water level. That's each. What do they tell us this time? At what rate is the water pouring in? So water pouring in is a volume. So that's dv dt that we're looking for. Pouring in is a volume. If the water level, so again, if, that's the given, if the water level rises at a rate of 1 centimeter per minute. So the water level is this guy, so how fast is it rising? So dh dt equals 1 centimeters per minute. So that's what we're given. That's what we want. We need an equation that relates the two. You kind of already had it from last time, right? We already did the work last time. It was this equation, right? It's volume connects the two. Volume of a cylinder is pi r squared times height, because the area of the base times the height. The base happens to be a circle. But then in this case, we know the radius has to be 4, so you plug that in, and you get this. Take the derivative with respect to time, and we got dv dt equals 16 pi dh dt, just like we did last time. This time, though, we have dh dt. It's 1 centimeter per minute. So we're going to sub that in. So that's a 1. So 6 times 1 is just 16 pi. Let's get our units correct. If you're not sure, it's volume. So it has to be centimeters cubed per second. Per minute, sorry. This one's in minutes. So that's the answer. If you're not sure why it's centimeter cubed, it actually makes sense mathematically. So this is a rate. So this is centimeters per minute. So where does 16 pi come from? That's the area of the base, right? It's 4 times 4. It's this guy, pi r squared. That's an area, so that's centimeters squared. So centimeters squared times centimeters gives me centimeters cubed. So that's where it comes from. I usually just look at what's going on. Oh, we're finding the volume, that's cubed. But it also works mathematically. Next one. Consider a rectangular bathtub whose base is 18 feet squared. How fast is the water level rising if the water is filling the tub at a rate of this? So I always like to draw it So we have a rectangular tub. Setting to this effect. Something like that. It's kind of slanted on the side there. Whose base is 18 feet. So we already know the area of the base. All of this is 18 feet squared because it's an area. How fast is the water level rising? So remember, water level is like how high is it going up? So this is my water level. So this is H. If water is filling the tub. So remember, anytime you're filling something up, that's your volume. So saying dV dt equals 0.7. And if you're not sure what that was volume, look at the units. Cubed. 100% volume. Right, if you're never sure, just look at the units. If it's to the first power, then it's a side of something. If it's second power, it's area of something. If it's cubed, it's a volume of something. That makes it easy. So that's our dV dt. What do we want? How fast is the water level rising? So how fast is this guy going up? So we want dH dt. So we have what we want. We have what's given. We have a picture. All we gotta do is find an equation that relates these guys, right? Related rates. Right, so we're talking about the volume here. So what's the volume of a cylinder? Sorry, of a cylinder, of a rectangular prism, is what I meant to say. And that is length times width times height. Right, that's how you find the volume, it's length times width times height. Or area of the base times height. And we already have the base, so we already have like these two. That's 18. They gave that to us, and we don't know the height. So that's our equation, right? Volume equals length times width times height, or area of the base times height, and we already have the area of the base. They gave it to us. How nice. So that's our equation. Now we just take a derivative of both sides with respect to t, as we always do in this lesson. On the left side here, derivative of v is 1, but wrong variable. On this side, you have 18h. Derivative of that's just 18, but again, wrong variable. So you get that. And then we just sub in what we have. The volume equals 0.7 feet cubed. So this is 0.7 equals 18 dH dt. Divide both sides by 18, so I get 0.7 divided by 18 equals dH dt. If you sub that into a calculator, you're going to get, sorry for my mess, 0.038. Now again, this is dH dt. So if you're wondering about the units, right, it's a side. So it's going to be singular. It's going to be power of 1 and then time. What we're talking about here. Feet per minute. So there's our answer. Right, it's always the same. Figure out what they give you, figure out what you want, find the equation that relates to those two guys, and then take a derivative with respect to time from both sides. Once you do that, it's just some calculus, and then plug it in. Another bathtub. Similar question, actually. Consider a rectangular bathtub whose base is 18 feet squared. At what rate is water pouring into the tub if the water level rises at a rate of this? So it's like the last one, but we just changed a couple things. So again, we have a rectangular bathtub. You don't have to draw a picture yet, but it's highly recommended. Hopefully better than my picture. Again, this is 18 feet squared because it's the whole area. We have a water level here. That's H. And this time, water is pouring in. At what rate is water pouring in? We're looking for dV dt. It's like the opposite of last time. If the water level rises, so dH dt equals 0.8 feet per minute. So again, we need an equation that relates that. We're doing volume, so volume equals area of the base times height. Or length times width times height. Either way, you're going to get this. Right, volume equals, they're given the area of the base, so volume equals 18h. Take derivative of both sides with respect to t. And we get, I'm going to go a little faster than last time, dV dt equals 18 dH dt. And this time, we have dH dt. This is 0.8. So we sub it in. And we get dv dt equals, sub into your calculator, you're going to get 14.4. And again, what do we do about the units? You can figure it out mathematically, or it's volume. So it's going to be feet cubed over minutes, because the units were feet per minute. So since it's volume, feet cubed. If you did it correctly, it should work out. So there we go. Next one. The radius of a circular oil slick expands at a rate of 2 meters per minute. How fast is the area of the oil slick increasing when the radius is 25? So we have a circular oil slick. So we're just talking about a circle here. Actually, I got technology. There we go. This is my circular oil slick. And it expands at a rate of 2 meters per minute. So the radius expands at meters. So dr dt expanding at a rate of 2 meters per minute. Very important. Right, so that's r, but they're giving us dr. The radius of circular oil expands at a rate of 2 meters per minute. Right, so they're not giving us r, they're giving us dr dt. So how fast it's growing. How fast is the area of the oil slick increasing when the radius is 25? So look what's going on here. They're saying they want the area, they want dA dt when the radius is 25. So low. So this says we're looking for the rate of the area, like how fast the area increasing when the oil slick is 25. Now that's a very important thing. It says when the oil slick, the radius is 25. So that's not before. It's not like before we could plug it in early. We have to plug this in after, because it says when it's 25. It's not always 25. So anytime it's constantly changing, this doesn't happen. We're going to do this after the derivative. So that's a very important concept. If it says when, if the thing you're talking about is changing, you cannot, it's not a constant. That means you cannot plug it in before you take a derivative. It has to be plugged in after you take a derivative. That's what it means by this. So now we need an equation that relates the radius and the area. Well, area of a circle is pi r squared. Now again, can I plug anything in? I don't know what the area is. The radius, I don't know what that is. I know what the derivative of that is, which is what we're looking for. And I can only plug this in after. Right, I cannot plug this in before because it says when it's 25. So all we do here is take the derivative with respect to t. Derivative a is just 1, but wrong variable, so dA dt. Pi r squared, remember pi is just a number. So treat it like a number. Bring this down, subtract 1 off. I get 2 pi r to the first, but don't forget wrong variable, so dr dt. So that's our equation, and now we can plug in everything we're looking for. I could plug in dr dt, 2. I could plug in the radius, because again, it says I want to know when the radius is 25. So after I take the derivative, fair game to plug it in. So now we're looking for specifically that time. And I have 2 and pi, that's all good, and I'm looking for this guy. So we're done. Simplify this. 25 times 2 is 50, times 2 is 100. So I get 100 pi. And then I don't forget your units. We're talking about area here, so this is going to be meters squared per minute. And there we go. The radius of the area is changing at 100 meters squared per minute. So that's pretty massive at when the radius is 25. Next one. I think it's the same. Actually, I should move. I think it's A and B, so I should keep it here. If the radius is 0 at time 0, how fast the radius is increasing after 3 minutes? How fast the area increase after 3 minutes? So again, we're looking for dA dt, but this time it's when time equals 3 minutes. That does change things slightly. So other than that, everything else is the same. We'll talk about if the radius is 0 at time 0. We'll talk about what that means in a second. But how do we set this up? Well, area equals pi r squared. Let's take both sides. When we do that, we get dA dt with respect to t equals 2 pi r dr dt. Alright, like that. Again, I went through it fast because we just did it up here. We're trying to find the area, so dAdt. Do we have dRdt? It's the exact same problem, so that's still 2. So nothing changed there. Right, where did I get that from? I got that from here. Still part of the same problem. Radius of a circular expands, right? My R is different though, right? Because this is B, it's not A. A had a radius of 25. B doesn't have one. B says if the radius is 0 times 0, how fast the area is increasing after 3 minutes. So my radius R equals 0, I time equals 0. But I need to know what R equals when time equals 3. So how do we figure this out? Well, what's going on? The radius is, look what the common part of the question is. The radius of a circular expands at a rate of 2 meters per minute. So every minute, it's expanding by a rate of 2 meters. So we're at 0. If we had a minute there, my radius would be 2 bigger. Because again, it expands at a rate of 2 meters per minute. So if we're at 0, 0, you add a minute, you add 2 meters to the radius. So that means that t equals 2, my radius will be 4. And at t equals 3, my radius will be 6. And that's the key here. So what's my radius going to be? Since it's been 3 minutes, and I expanded at a rate of 2 meters per minute, it's going to be 6. Multiply it all together. 2 times 6 times 2 pi gets me 24 pi. And again, we're doing area, so meters squared per minute. And that's the answer there. 5. Assuming that the radius r of a sphere expanded at a rate of 14 inches per minute, the volume of the sphere is given by this. Determine the rate at which the volume is changing with respect to time, r equals 8. So let's just like read it again, right? Assuming the radius of a sphere. So we're talking about a sphere here. Best way to draw it's like this. Is expanding at a rate of 14 inches per minute. So we're given is the radius is expanded at a rate, so dr dt. You can tell if it's a fraction, it's a rate, right? It's not just r equals 3, it's r equals, it's a radius, it's a rate's 14 inches per minute. So dr dt equals 14 inches per minute. The volume of the sphere. So that's helpful. We need that. So volume equals 4⅔ pi r cubed. Right? It's good for our relation. What do we want though? Determine the rate at which the volume is changing with respect to time. So we're looking for V. So we want, I should say, the rate at which it's changing. So we're looking for dV dt at r equals 8. Again, when r equals 8, right? So anytime it says when, or like it implies like a when, it's this thing is changing, but we only care about when it's r equals 8. Since it's changing, I can't plug it in before. I gotta wait till after I take the derivative. Anytime we see that, it's after d of dt. Right? So this is something that's changing, but I want to know at the specific time, so I gotta wait till after the derivative. So there's everything we have. So we just gotta take a derivative. So we're gonna take d of dt. Left side derivative v is 1, but wrong variable. So dv dt. On the right side, we have this. So bring the 3 down, subtract 1 off. You get 4 pi r squared. Don't forget wrong variable. So dr dt. Right, so we have that. And now we can plug in what we have. So what do we know? We know dr dt is 14. So this guy is 14. And now I can plug in my r, since after I took the derivative. So I want the r for specifically at 8. So 8 squared. So multiply all this together. 4 pi times 64 times 14. And you get 3,584 pi. That's what my volume is. That's the rate of my volume. That's how big it's expanding. And again, units, since we're doing volume, it has to be cubed. So it'll be inches cubed per minute. So it looks like this. So there we go. I'm not sure why I went away. Okay. 6. Assume that the radius of a sphere is expanded at a rate of 14 inches per minute. So we're doing another sphere problem. The volume of the sphere is given by this. Yeah, we know that. Determine the rate at which the volume is changing with respect to time at t equals 2 minutes. Assume that r equals r at t equals 0. So kind of the same concept we did a little earlier. So let's talk about what we want and what's given. I flipped it a little bit today in the first problem. So given, we know that the radius is expanded at a rate of 14 per minute. So dRdt is 14 inches per minute. And what do we want? We want the volume with respect to time at t equals 2. So we want dV dt, the rate at which the volume is increasing, right? It's not that the volume, it's the rate of volume, so it makes it dV dt. We want that at t equals 2. And just like before, they tell us, hey, the rate is 0 and time equals 2. In that case, when time equals 1, what's the radius? Well, we're growing 14 inches per minute, so that'd be 14. And then when time equals 2, my radius would be 28. I can do math sometimes. So this is just means the radius equals 28. Again, if you know what the rate is, you can multiply by time and get your answer there. I'm just trying to show you like the thought process. So basically, we start with this, our volume that connects the two ideas, 4/3 pi r cubed, and we want to take the derivative of this. Now, do I plug in the r before or after? Determine the rate at which the volume is changing with respect to time at t equals 2. So it doesn't say like specifically when like the other ones do, but again, you cannot plug this in before. The general idea is if it's changing, you can't plug it in before the derivative. You can only plug in constants before the derivative. And this radius here is changing. That's the whole point of this problem, right? It's expanding, it's getting bigger. So like how right here we had 0, now it's 14 and 28. So I cannot plug this in before the derivative. You can only plug in constants. So I'm just going to leave it like that. I'm going to take our derivative with respect to t. The derivative v is 1, but dv dt. Over here, right, there's only one variable, that's r, so bring it down, subtract 1 off. So you get 4 pi r squared. Don't forget, wrong variable, dr dt. And now we can plug everything in. So 4 is just 4, pi is just pi, r is 28, so we can square that. And then dr dt, they told us is 14. We'll apply it all together. I would use a calculator. 43904 pi. And then my units, again, we're doing volume here, so it's cubed. And what was it? Inches cubed per minute. So there we go. That's the lesson.